First, let's reset the Pythagoras against the left post. Take note that this area here, if we divide it with a diagonal from the leftmost upper corner to the rightmost lower corner, then the triangles will represent the gold beads on the bottom of the Pythagoras, which there are 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the squares above those triangles will represent the brown beads. And so you'll see when we manipulate the beads on the triangle, we will have corresponding areas defined by intersecting lines. Here. But there will be a correspondence along this diagonal, exactly mapping to the positioning of the gold beads on the bottom of the Pythagoras triangle. And then we'll count from right to left 7 beads and displace those to the right, giving us a line, an area defined by horizontal and vertical line that will equal 7b of the equation. Bx will be 7x. Now, we will count over 5 beads and displace those beads, creating 2 intersecting orange lines, giving us 2 times 5, 10 for C1. And we can see here 2 times 5 gives us the 10. So we have x squared minus 7x plus 10. So we're going to push over another bead, 6 from the right. And that will give us intersecting green lines and give us for y 4. So we have x squared minus 7x plus 10 equals 4. And this 4 we can see elbowing around the intersecting orange lines. We have 4 squares. If we look over, so there's our 10. And then we're going to show the 10 looking at the intersecting yellow lines as boundaries. We see 2 halves and we go up elbowing around the intersecting orange lines, and we see 4 in the corner, 2 making 6, 2 more making 8, and the 2 half ones bounded by the yellow lines giving us 10. So this area elbowing around the intersecting orange lines will give us 10. And now the 4, we will see at the inner part between the green and the yellow, we have 1, 2.5 this way, and that gives us a 4. And for the next step, In completing the square, we will subtract that 4 from each side. So this 4 right here, bounded by the intersecting yellow lines, we will subtract. And when we subtract that 4, we get 6. The 6 that is elbowing around the intersecting green lines, as you see here. The 6 here, 10 minus 4, giving us 6. And we will continue, and we will take half of 7, which is B, and square that half, 3.5, and we get 12.25, which we add to each side of the equation, and then we subtract 6 from the right side of the equation. And so, if we look at 3.5, which is half of the blue line, we can see this area in here is 12.5. You can see. .5 going up 3.5. You see that little bitty square right there is the 0.25. So 3.5 times 3.5 will give us 12.25, which we added to both sides. Here we can take another look at it. 3.5, 3.5 times 3.5 will give us the area of 12.25. Now take away 6, and that will be the 6. Take away 6, and that will give us this area remaining, which will equal to 6.25. The area here bounded by the intersecting yellow lines and the intersecting green lines. That will be the 6.25. Here again, this area bounded by the intersecting green and yellow lines. You can see that little 0.25 in the corner, and we took away this 6 here from the 12.25, and that left us the 6.25 here, bounded by the intersecting green and intersecting yellow center lines. There we have the 6.25. Next up, we'll take the square root of the 6.25, and we'll get 2.5. And we see we have 3.5, which of course is half of B, 7. Here again, 3.5, 3.5. .5. See the 2.5 here. 1, 2.5. 2.5. And we can see it again up here. 1, 2, 2.5. That is, of course, the square root of 6.25. Now let's do the next step of completing the square. And we have x equals 3.5 plus or minus 2.5. And if we look here, we have 3.5, which is half of 7, as pointed out before. Now here is 2.5. We take that away from the 3.5, we're left with 1. So 3.5 take away 2.5 leaves us 1. Look to the other side of a yellow dividing line. We'll see we have 3.5 on the other side. And we can add 2.5 to that. And then we have 2.5 plus 3.5 will give us 6. So our solutions are 1 and 6. There we have it. 1 and 3.5 plus 2.5, 6. There we see how we have mapped this area onto the numerical completion of the square. As pointed out at the beginning of the video, there's a correspondence between the gold beads on the bottom and the triangles along the diagonal here. And you will see that here we have one triangle corresponding to this gold bead. And then we have 1, 2, 3, 4, 5, 6 corresponding to these gold beads. And these also correspond with the size of the squares here, where we have 1 square and 6 squares that have given us our roots for our equation, which also given here, our roots being 1 and 6. And so in this way, we have an equivalence between the areas partitioned by repositioning the beads on the abacus and the areas sectioned off here with the intersecting orange, green, and blue lines. Now, one of the things which is necessary when working with quadratics is to be able to graft the curve. And that is possible from the information provided in this area. As we've seen before, the area 6.25, which is K, which corresponds to the Y position of the maximum or minimum of the curve, is given by this inner area here, bounded by the intersecting yellow lines and the intersecting green lines. And this will always be the case when generating these partitioned areas. And of course, we are also given the vertex by taking half of B, which in this case was 7, and the half of that being 3.5. And of course, other areas, including the 6 here, which will be our y-intercept, are given by this elbow of areas, this area elbowing around the intersecting green lines and being bounded by the yellow line. So in this way, this area which is generated by mapping the repositioning of the beads in the Pythagoras to it are sufficient, these areas are sufficient to give us all the information we would need to graph the curve of a quadratic and to find its roots. Here is another example. First, we'll push over 6 beads. Then we'll push over 4 beads, giving us intersecting orange lines. And then we'll push over a bead in the 7th position, giving us intersecting green lines. Now let's complete the square. And we can see now that we want to investigate the areas to see if we have all the information we need to graph the curve of the equation x squared minus 6x minus 7 equals 0. And the roots we have will be given by the total number of beads, which we can see here is 7, and it's represented here as the total number of squares. And since we have, and this will be a positive amount, a positive 7, and the other root will be given by the number of beads that exceed the intersecting blue line, which represents the b variable in the equation. And we see we have 1, and it will be minus 1. So our roots will be minus 1 and 7. Because 1 times minus 7 equals 7. And the sum of them equal minus 6. Now we have the roots. Then we, of course, also would need the y-intercept, which of course is given by minus 7, which we can get here also. Minus 7, or 7. Minus 7 is the y-intercept. And we can then we need k, the vertex. And since we have this bisecting yellow line of b, and we can see that the vertex, and here is blue representing the square of b, and we'll see that half of b is 3, and its square is 9. And so the vertex will be at 3. And then we need k. And as pointed out previously, k will be bounded by the intersecting yellow lines, and we said the intersecting green lines, but we have 2 sets of intersecting green lines here. One intersecting is coincidental with the blue intersecting lines. And so we will not, the bounding area will not be bounded by the intersecting green lines that are coincidental with the blue. It will be bounded by the green lines that are not coincidental with the blue. So we say that K should be equal to all of this area from here and bounded here, and it's 16. And if we look over here, we can see that K does equal 16, and the square root of K is plus or minus 4. And so, which gives our roots as being equal to 3 plus or minus 4, which of course will give us 7 and minus 1, as is indicated here. 7 and minus 1. The minus being determined because this area exceeds B, the blue. If the area was inside blue, in the blue, it would be positive. When it exceeds blue, as in this case with the beads, we pushed over first 6 beads, and then we pushed over 7 beads, and so this area outside of it becomes negative. And so in that way, here's another example how we can use areas that can be mapped onto the positions of the beads on the Pythagoras and its areas to get all the information we need to graft a quadratic equation, as we can also see that information correspondingly in the completion of the square.